Assalamu alaikum dear students. Today we are going to discuss Sylow-p Subgroup and we will try to prove Sylow first theorem. Okay, what is the definition? Sylow-p Subgroup. Let G be a finite group, means order of G is equal to n. Of course, n is a finite number, right? And P divides order of G. Of course, where P is a prime number, where P is a prime number, P is prime. Okay. Let G be a finite group of order n, and P be any prime divisor of n. A subgroup H of G is said to be a Sylow-p subgroup if order of H is equal to P power alpha, where alpha is positive, alpha could be greater than or equal to 1, right? And secondly, P power alpha divide n. This is a trivial condition. Of course, if you are saying order of H is equal to P power alpha, then by Lagrange Theorem, this is very easy condition that order of H divides order of G. So this condition is trivial if you write or not. P power alpha divide n, but P power alpha plus 1 does not divide n. No higher power of P will divide order of G. Means that P power alpha is the highest power which is a divisor of order of n. Right? So you can merge these two, that P, if P power alpha divide n, of course this is true because H is a subgroup, and by Lagrange theorem we know that P power alpha divide n, but P power alpha 1 plus 1 does not divide n. Okay, you know a little number theory that if P power 100 divide n, then of course P power 99 will divide n. This implies P power 98 will divide n, and so on. P square will divide n. This implies P will divide n. Okay? Means if a higher power will divide a given integer n, then all its lower power must also divide n. However, if P will not divide n, then P square and higher power, none of the higher power will divide n. Because if any higher power is dividing n, then of course all the smaller powers also dividing n. It's a little bit number theory. So similarly, if you are saying that P square does not divide n, if P square does not divide n, then of course P cube will not divide n, because if P cube divide n, then P square must divide n. So if I am saying that conversely, that P square does not divide n, this means that no higher power of P other than 2 will divide n, because if any of the higher power will divide n, then all the smaller powers must also divide n. So because it is sufficient to say that P power alpha 1 does not divide n, this means that no higher power of P will divide n. Means that P power alpha is the highest power of the prime number P, so that P power alpha divide n, and no higher power of P will divide n. So it is sufficient to write that P power alpha plus 1 does not divide n, because I have shown you that if P power alpha 1 plus 1 does not divide n, then of course P power alpha plus 2 and P power alpha plus 3 and no higher power will divide n as well. Okay? So again, so you can summarize the definition. What should be the definition? The definition is, let G be a finite group and P any prime divisor of order of G, then a subgroup H of G is said to be a Sylow-p subgroup if order of H is equal to P power alpha with p power alpha plus 1 does not divide n. So you can summarize this that if order of h is p power alpha, of course where alpha is greater than or equal to 1, where alpha is greater than 0, with p power alpha plus 1 does not divide n means that p alpha is the highest power for which p power alpha divide n. Since h is a subgroup, so by Lagrange theorem, this is very much clear that p power alpha divide n. Okay, so let's check with the help of some particular example about Sylow-p subgroup. Let order of G is equal to 100, then you know that we can write 100 as 2 square into 5 square. Okay, so let order of H is equal to 2. If order of H is equal to 2, then see 2 divide 100, but 2 square also divide 100. So H cannot be a Sylow-p subgroup in a group of order 100. Hence, so we have the definition that if 2 divide 100, then 2 square and no higher power of 2 should divide 100. But here, if order of H is 2, then 2 divide 100, also 2 square dividing 100. So this means that there does not exist any Sylow-p subgroup of order 2. Hence, in this case, H is not Sylow-p subgroup. Why? If order of H1 is equal to 2 square, look at this. If order of H1 is equal to 2 square, then 2 square is a divisor of 100, and but 2 cube does not divide 100. Okay, so here 2 square divide 100, but 2 square plus 1 does not divide 100. We know higher power of 2 other than 2 is dividing 100. So H1 is a could be a Sylow-p subgroup, right? H1 could be a Sylow-p subgroup. So H1 is a Sylow-p subgroup. Similarly, for 5 square, Sylow-5 must be of order 25, because if k order of k is 5, then k is not a Sylow-5 subgroup, because 5 is dividing 100 and 5 square is also dividing 100. We are saying that if order of k is 5 and the power of 5, that is 1, is the highest power, which is dividing 100, then it is a Sylow-5 subgroup. But you see that 5 square is also dividing 100, so any group of order 5 is not a Sylow-5 subgroup in a group of 100, right? But if order of k1 is equal to 5 square, then of course k1 is a Sylow-5 subgroup. Okay, so let's have some other examples. So you take, let order of G is equal to 80. Okay, so 80 can be expressed 2 into 2 into 2 into 2 into 5. That is 2 power 4 into 5. Okay. So if let H1 is of order 2, then this is not a Sylow-p subgroup because 2 square also dividing 80. So H2 of order 2 square. This is also not a Sylow-p subgroup because 2 power 2 plus 1 also divide 80. So H2 is not a Sylow-p subgroup. If there is this another subgroup H3 of order 2 cube, then again this is also not a Sylow-p subgroup because 2 cube plus 1 also dividing 80, order of G. So you cannot have any subgroup of order 2 as a Sylow-p subgroup. Any subgroup of order 2 square is not a Sylow-p subgroup in a group of order 80. Any subgroup of order H is not a Sylow-p subgroup in a group of order 80. So H4, if order of H4 is 2 power 4, yes, it means that H4 is a Sylow-p subgroup order 16 because 2 power 4 is the maximum number which is dividing 80. You see 2 power 4 into 5. So here 2 power 4 divide 80, but 2 power 4 plus 1 does not divide 80. This means that H4 is a Sylow-p subgroup of order 16. So from here, from the prime factorization of your number, you can see that there could be a Sylow-p subgroup. If there is a Sylow-p subgroup of order, then its order must be 16. Similarly, if there is a Sylow-5 subgroup, then its order is 5. So similarly, order of K1 is equal to 5. Then of course 5 divide 80, but 5 square does not divide 80. So K1 is a Sylow-5 subgroup of order 5, right? So this is a definition of Sylow-p subgroup. What we have learned that let G be a finite group of order n and P be any prime divisor of order of G. If you have a subgroup H of order P power alpha such that P power alpha does not divide P power alpha plus 1, mean P power alpha is the highest number which is dividing n, means that P power alpha plus 1 does not divide order of G, or you can say that if P power alpha is a divisor of order of G, then no higher power of P would divide order of G. So in this case we are saying that H is a Sylow-p subgroup, right? Okay, and we will see another definition is okay, if you see from order of G is equal to 80, which is 2 power 4 into 5, and if H is a subgroup of order 2 power 4, then what is index of H in G? This is, what is index of H in G? This is order of G by order of H, which is equal to 2 power 4 into 5 divided by 2 power 4, which is 5. So look at this. So clearly index of H in G and 2, index of H in G and 2 is equal to 5 and 2, which are relatively prime. So what I am saying that if order of H is equal to P power alpha and H is a Sylow-p subgroup and H is a Sylow-p subgroup if and only if index of H in G with P is 1. Right? So this is another definition. We have an alternative definition that any subgroup H of order P per alpha is a Sylow-p subgroup if and only if index of H in G with that prime number is 1. So GCD, highest common divisor of these two numbers, should be 1. Look at this. 2 power 4, order of G by, so we will cancel out 2 power 4, this is 5. And 5 and 2, you know 5 and 2 are relatively prime because these are the different primes in its canonical form. I mean to say that in its prime factorization, which is also known as canonical form. Okay. So we have another definition is that if H is a Sylow-p subgroup of order P power alpha, then index of H in G with P both are relatively prime to each other, right? So write the definition, alternative definition. This is another definition. Let order of G is equal to n and P divide n, where P is prime. Let order of H is equal to P power alpha, right? We say that H is a Sylow-p subgroup in G if index of H in G with P is 1. This is equivalent condition of saying that no higher power P would divide order of H, because if on contrary, you see, if order of H, index of H in G, P is equal to some P, you know that this is any other number, and relation between any number with prime is that either P divide that number or P and that number both are relatively prime. So if they are not relatively prime, then P must be divisor of this. So if P is a divisor of this, then their GCD must be P. This means that P is dividing, this means that P is dividing index of H in G, which is equal to order of G by order of H. So this implies P will divide, what is order of G? Order of G by, okay, we can write like this. If P divide index of H in G, then by Lagrange Theorem, order of G must be equal to order of H into index of H in G, right? If P divide index of H in G, then this implies that index of H in G must be equal to some Pt. So put here where T belongs to G. So put here, this is P power alpha, this is P T, which is equal to P power alpha plus 1T. So order of G, this implies that P power alpha plus 1 divide order of G, which is a contradiction against the fact that H was a Sylow-p subgroup, right? So we have shown that if P divide index of H in G, you know that with prime number, any other number is either relatively prime to P or P is a divisor of that number. You can check. Say fix some number 3. 3 with 2, both are relative prime. 4, 3 and 4 are relative prime. 5, 3 and 5 are relative prime. Yes, yes. For 6, 3 divides 6. For 7, relative prime. For 8, relative prime. For 9, 3 divide 9. So look at this. This means that a prime number has either two relation with any other number. Either p and that number are relatively prime to each other, or p is a divisor of that number. Now we are saying that if index of h in G is not relatively prime to p, then p must be a divisor of index of h in G. Then index of h in G must be equal to some pt. So by Lagrange theorem, order of G is equal to order of h in index of h in G. So putting the values, this is pt, this is p power alpha, this is p power alpha plus 1t. Again by definition of Vn, because this number n is equal to some p power alpha plus 1 into t, this means that p power alpha plus 1 must divide order of G, right? So you have a contradiction, because we have supposed that H was a Sylow-p subgroup with order p power alpha, and by definition e power alpha plus 1 dividing the order of G, then H would not be a Sylow-p subgroup. Hence you have a contradiction. That's why this is not the case. So P can never divide index of H in G if H is a Sylow-p subgroup. That's why index of H in G with P both are relatively prime to each other. So this is another alternative definition. Means to say that this is equivalent to saying that p power alpha plus 1 does not divide order of G. So you have another definition. Whenever you need to show that H of order p power alpha is a Sylow-p subgroup, you just show that index of H in G is prime to P. Okay, so let's check with the help of some other examples. Okay, you can check this definition as well. Suppose G is a group of order 75. Suppose order of G is equal to 75, which is equal to 3 into 5 square. So if order of H is equal to 3, then what is index of H in G? So order of G by order of H, which is 3 into 5 square, which over 3, then 5 square. So thus index of H in G with P, what is P here? P is here 3, because you want to discuss a 3 group in a group of order G. So this is 5 square and 3, both are relatively prime. Yes, H is a Sylow 3 subgroup. Yes, H is a Sylow 3 subgroup. Now, if you take H1 of order 5, then what is index of H1 in G, which is order of G by order of H1, which is 3 into 5 square by 5, 15. And here index of H in G with P 15, 5. This is not relatively prime, because 5 is dividing 15, GCD is 5. So GCD is 5, which is not equal to 1. So this is not a Sylow 5 subgroup. You cannot have a Sylow 5 subgroup of order 5 in a group of order 75. Okay, so if you put 5 square, then it will work, because index of H in G would be equal to 3, and 3 and 5 are relatively prime. So a group of order 25 is in fact a Sylow 5 subgroup in a group of order 75, right? So now we have First Sylow theorem. What is that theorem? We will write its statement, and we are going to prove this. See the first theorem. Statement a finite group whose order is divisible by a prime P contains a Sylow very simple definition. Suppose G is a finite group. Let order of G is equal to n. If any prime P divides the order of G, then that group G must has a Sylow-p subgroup. Okay, so you could have another definition or another statement. Let order of G is equal to P n and P power alpha divide order of G where alpha is greater than 0, then G has a Sylow subgroup of order P power alpha. Of course, here I am saying that P power alpha is the highest power. Alpha, this is very much trivial that when I am saying that P power alpha divided order of G, I am considering the maximum power. Otherwise, I should write P power T, okay, where T is greater than alpha. So, if you write like this, that order of G is n and P power alpha divides order of G, or you can say that with alpha is the highest power, then of course then G has a Sylow-p subgroup order P power alpha, right? Keeping in view that P power alpha plus 1 does not divide order of G, so there is no ambiguity to write P power alpha plus 1 does not divide order of G. This is again the definition of Sylow-p subgroup. So if you have such a subgroup whose order is P power alpha with no higher power of P divides order of G, of course then G has a Sylow-p subgroup of order P power alpha. So this is not the necessary condition. Without this condition, we can show that G has a Sylow-p subgroup of order P power alpha. So in this case, you need to show that P power alpha plus 1 does not divide order of G. So that would fulfill the definition. Okay. Or simply without these two statements, we can have a simple statement. Every group of order n must contains at least one Sylow-p subgroup corresponding to every prime factor P of G. Okay, this is more clear version, right? P is any prime divisor of order of G. Then G must has at least one Sylow-p subgroup, right? So this means that corresponding to a prime P, a group G has more Sylow-p subgroups, but we will see that these must be conjugate to each other if their orders are same in Sylow-p subgroup. Like S3, order of S3 is equal to 6, which is equal to 2 and 3. So look what this theorem says. This theorem says that S3 must contain a Sylow-p subgroup. Similarly, S3 must contain a Sylow-p subgroup, right? So in S3 you have a Sylow-p subgroup, you have a Sylow-p subgroup. And similarly, D4, which is equal to 8, that is 2 cube. Look at this. D4, 2 cube. So this could not have a Sylow-p subgroup of order 2, Sylow-p subgroup of order 2 square. So it's a Sylow-p subgroup. It's itself a Sylow-p subgroup of order 8, right? Similarly, S4, order of S4 is 24. That is 2 cube into 3. Yes, this means that S4 has a Sylow-p subgroup of order 8. So now question is whether that Sylow-p subgroup is isomorphic to D4. Okay, but here is another group of order which is Q8. So you need to see that whether the Sylow-p subgroup of order 8 is isomorphic D4 or not. So there is a Sylow-p subgroup. There is a Sylow-p subgroup in S4, right? So this is our first statement, is that you just write the order of a group. Okay, if any prime number P divides the order of G, then that group must has at least one Sylow-p subgroup. Okay, so now we prove this theorem. Okay, again, just like Cauchy first theorem, Cauchy second theorem, we will try to prove this with the help of induction. If G is equal to N and N is equal to P, then P is a prime number. Of course, G itself a subgroup of itself, a P subgroup, and you know P is the highest power, which is dividing the order of P, order of G, which is P. P square does not divide P. So theorem is trivially true. Next we will suppose that theorem is true for all groups of order less than n, which are of course divisible by P. Means that whenever there is a group whose order is less than n and whose order is divisible by P, there must be a Sylow-p subgroup. Okay, and we will try to show that our theorem is true for order n as well, right? So okay, try to prove this. Let G be group of order n and P power alpha be the highest power of the prime P dividing n. Let G be a finite group of order n and P power alpha be the highest number such that P power alpha divide n, mean P power alpha or alpha is the highest power, you can say that alpha is the highest power such that P power alpha divide order of G. Okay, so we apply induction on the order of G. Okay, we apply induction. This induction is just like as we have used in Cauchy first theorem and in Cauchy second theorem. So similarly we will prove this theorem. Okay. If n is equal to p, then G itself a p group. So if n is equal to p, then G is itself a p group. Okay, remember that a Sylow-p subgroup. Sylow-p sub is a p group as well. There is no ambiguity, right? Hence, H, which is equal to G, is a Sylow-p subgroup of G. Means G is itself a Sylow-p subgroup. G is itself a Sylow-p subgroup. Next, we suppose that theorem is true for all groups of order less than n and divisible by p. We suppose that theorem is true for all groups of order less than n with p divide n less than n and divisible by p. Mean you have a number which is less than n and also divisible by p. So whenever you find that the order of G is lesser than n and p is a divisor of that number, then by induction hypothesis there must be a Sylow-p subgroup. Okay, so this is our inductive step, our induction hypothesis. So let G be a group of order n. Let order of G is equal to n and p divide n. Okay, just like Cauchy's theorem, we will consider two possibilities, that there is a subgroup whose index is prime to p and every subgroup whose index is divisible by p, or there is a subgroup whose index is divisible by p and all subgroup whose index are not divisible by. So these are the two possibilities. I mean that p divide order of G and p does not divide order of G. This is our supposition. So we consider the two possibilities just like Cauchy 1 and Cauchy 2 theorem. There are two possibilities. Number one, this is a subgroup PH of G with index prime to P. PH of G such that index of H in G with P is equal to 1. Number two, all subgroups whose there is no subgroup H whose index is prime to P. Mean whenever there is a subgroup, its index must be divisible by P, right? So the second possibility is that there is no subgroup H of G whose index is prime to P. There is no subgroup H of G such that index of H in G and P is not equal to 1, or using that every subgroup H has index divisible by P. Okay, of course. And also remember that if P and index of H in G is divisible by P, then P must be a divisor of order of H. And if P and index are not relatively prime, so means that P is a divisor of H, so P and H are relatively prime. We will discuss both the cases separately. Okay. In first case, we can write with the help of induction hypothesis. Case 1, right? The order of H is less than of G. Okay. When here order of H is less than order of G, since H is a subgroup of G. Also, index of H in G and P are relatively prime. So by Lagrange theorem, order of G is equal to order of H into index of H in G, right? Now P divide order of G, P divide left side, so because P divide right side, but index and P are relative prime, so P must divide order of G, right? Order of H. Now, since P divide right hand side, left hand side, so P divide right hand side, that is P divide order of H into index of H in G, but P and index of H in G are relative prime, so this implies P divide order of H. Now look, order of H is less than order of G, less than n, which was supposed to be n. You have supposed that order of G is n and P is a divisor of order of G, right? Now order of H is less than n and P is a divisor of order of H. Hence, by induction hypothesis, H must has a Sylow-p subgroup, right? Hence, by induction hypothesis, H has a Sylow-p subgroup. Hence, by induction hypothesis, H has a Sylow-p subgroup. H has a Sylow-p subgroup. And further, since index of H in G and P are relatively prime, so a Sylow-p subgroup of H is also Sylow-p subgroup of G. Okay, we need to check this, what I am writing there. I am saying that if index of H in G is prime to P, then every Sylow-p subgroup of H is also a Sylow-p subgroup of G. Means that you need to show that if index of H in G is relatively prime with P and H is a Sylow-p subgroup in G, then K is a Sylow-p subgroup in H, then K must also be a Sylow-p subgroup of G. Okay, we could have a separate result. So I need to show that if index of H in G is equal to P and H is a Sylow-p subgroup in G, then if K is a Sylow-p subgroup of H, then K is a Sylow-p subgroup of G. Now we can show this easily. There is no problem to show this simple result. And suppose order of G is equal to n. Okay, I want to show here. Suppose order of G is equal to n and index of order of H is equal to P power alpha, right? Order of H is equal to index of H, you can say index of H in G1. Suppose we write index of H in G is equal to K1 and order of H is equal to K2. Say, suppose order of G is equal to n, index of H in G is equal to K1 and order of H is equal to K2, then by Lagrange theorem. By Lagrange theorem, n is equal to K1, K2. You know, multiplication of order and index is equal to order of G. This is our Lagrange theorem. K1, K2 is equal to n. Now suppose, so let P be a Sylow-p subgroup in H with order of, you can say P star, you can assume some other number, M, you can suppose M, let M be a Sylow-p subgroup. You write M because we are using this prime as well. Let M be a Sylow-p subgroup in H with order of M is equal to P power alpha, alpha greater than 0. This means that P power alpha is the highest number which is dividing K2 and no higher power alpha would divide K2 because you have taken that M as a Sylow-p subgroup in H. What we want to show that if index of H in G is P, then a Sylow-p subgroup of H is also Sylow-p subgroup of G. Means that P power alpha divide K2, but P power alpha plus 1 does not divide K2, and we want to show that P power alpha divide N and P power alpha plus 1 does not divide N. So here we are given that P power alpha divide K2, but P power alpha plus 1 does not divide K2. We need to show that P power alpha divide n, but P power alpha plus 1 does not divide n. You have supposed that M as a Sylow-p subgroup in H, right? M is a Sylow. Let M be a Sylow-p subgroup in H with order of M is equal to P power alpha. Of course, P power M alpha divided order of H, and P power alpha plus 1 does not divide order of H. But we want to show that M is also a Sylow-p subgroup of G due to index and P are relative prime. So we will use the concept index is relative prime with P, and we will show that P power alpha plus 1 does not divide n. P power alpha divides n, it is clear, because K2 divide n and P power alpha divide K2. So by transitivity, P power alpha divide n. Here, note that P power alpha divide order of H. Of course, M is a subgroup of H, so which is equal to K2, and order of H divide order of G, that is K2 divide N. So look, P power alpha divide K2 and K2 divide N. So by transitivity, first condition is clear. So by transitive indivisibility, P power alpha divide n. So one thing is satisfied. Now we need to show that P power alpha does not divide n. So we can also show this. There is no problem. Okay, see that we have n is equal to K1, K2, okay, number one, since P power alpha divide order of H, which is K2, so this implies K2 is equal to P power alpha T, where T belong to Z, and T and P are relative prime. This is very much clear. If T and P are not relative prime, then GCD of T and P would be equal to P. This means that P divide T, so T must be equal to some T1P, so which is P power alpha plus, so P power alpha plus 1 divide K2. This is not the case, that's why T and P are relative prime. Because if T and P is not equal to 1, so this implies T and P would be equal to P. This implies P divide T. This implies T is equal to P T1. Put here, so you are getting K2 is equal to P power alpha P T1. So K2 is equal to P power alpha plus 1 T1. This implies P alpha plus 1 divide K2. A contradiction, right? So that's why T and P are relative prime. This is very important condition. So since P power alpha divide K2, so K2 is equal to P power alpha T because of the definition of division. So here P and T are relative prime. If they are not relative prime, T and P are not relative prime, so T and P would be equal to P, means P divide T. So T is equal to PT1. Put here, so K2 is equal to PT1, that is P power, so P power alpha divide K2. A contradiction because P power alpha is the highest power which divide order of H. So that's why T and P are relative prime. Okay, yes, this is clear. Putting in 1, values in 1. What is this? This is n is equal to k1 and this is p power alpha t. Okay, so this imply n is equal to p power alpha k1t. Now we will prove this theorem if we show that p and k1t are relative prime. If I can show that p and k1t, so you cannot produce any p from here, that's why p power alpha will divide n, right? This means that p power alpha plus 1 can never divide n. So the idea is to show that p and k1t both are relatively prime. Okay, so we need to show, to prove our claim, p with k1t are relatively prime, right? And we can show very easily. What is k1? What is k1? Note that k1 and p are relatively prime because k1 is index of h in G, and you have supposed that index of h in G is prime to p. Okay, so this is given in case 1. This k1, or you can say like this, given index of h in G with p is equal to 1, this implies k1p is equal to 1. Also, you have assumed that tp is equal to 1, so this implies k1t with prime p is equal to 1. Yes, this is true. This is true because p is a prime number, and if a and p are 1 and b and p are 1, then a, b and p are 1, because I can show you if a and p is 1 and b and p is 1, then a, b and p is 1. For otherwise, if not, p would divide ab. This implies p would divide a or p would divide b. This implies either p and a is equal to p or p and b is equal to p. So which is a contradiction, right? Because a and p is equal to 1 and b and p is equal to 1. This implies a, b and p is equal to 1, the GCD. If not, then p, a, b and p, I can write clearly. If a and p is equal to 1 and b and p is equal to 1, this implies a, b and p is equal to 1. If not, then a, b and p would be equal to p. You know, GCD with prime number must be p. Any prime number with any other number is either relative prime or is a divisor of that number. So, a, b and p is equal to p. So this implies p divide a, b. So this implies p divide a or p divide b. This implies p and a is equal to p or p and b is equal to p. So look, this is a contradiction because you are given that AP is equal to 1 and BP is equal to 1. That's why if K1P is equal to 1 and TP is equal to 1, then clearly you have shown that K1T is equal to TP is equal to 1. So by equation 1, by 1 you have n is equal to p power alpha k1t, but k1t p is equal to 1. This implies P power alpha divide n and P power alpha plus 1 does not divide n. Hence, K is a Sylow-p subgroup of G as well. M, sorry, not K, this was M. Right. So this was due to first case. We have supposed that if index of H in G with P both are relative prime, our GCD is 1, then every Sylow-p subgroup of H is serving as a Sylow-p subgroup of G as well. But remember, if this is not the case, then a Sylow-p subgroup of H can never be a Sylow-p subgroup of G as well. Okay, so we have proved our first case. Now come to the second case, which is quite easy. Case 2. Case 2 is every subgroup G has index divisible by P. So in particular, you repeat the same story as we have given in center of P group is non-trivial, then Cauchy first theorem, then in Cauchy second theorem, till that center of G is either P or multiple. The order of center of G is P or multiple of P. You take the consider the class equation just like Cauchy's second theorem, right? Or you can directly write, we know that if P index of if P divide index of H in G for every H, then it is easy to show that center of G, order of center of G is P or multiple of P. See last lecture. Of Cauchy second theorem proof. Okay, I already have proved in Cauchy's second theorem's proof that center of G, order of center of G is P or multiple of P. You can write till you take consider the class equation, then write n is equal to m1 plus m2 plus so on. Since each mi on the right side is the index of normalizer, and normalizer is a subgroup, and every subgroup the index of normalizer. Each mi on the right side, index of normalizer, like you have n is equal to m1 plus m2 plus so on plus mr. This is the class equation. Each mi on the right side is in fact the index of normalizer, and index of normalizer divisible by P. So each on the right side divisible by P, left side is divisible by P. But remember, from the right side you have some self-conjugate element. At least you have identity element. If there is exactly one self-conjugate, then all these divisible by P, P divide n, so P will divide 1, which is a contradiction. Hence there must be more than one, the minimum P or multiple of P self-conjugate element, so that the equation is balanced. So we are at the step. Then it is easy to show that order of center of G is P or multiple of P. Okay, I am at this step. Next idea is easy. Hence, by Cauchy's first theorem, since center of G is abelian, so by Cauchy's theorem, center of G has an element of order P. You know, this means that P divides order of G. This imply P divide order of center of G, and since P divides order of center of G is abelian, no need to say abelian because we have Cauchy's second theorem as well. So this is sufficient reason. Since P divides order of center of G, since our center of G is order of center of G is P or multiple of P, we have shown already in Cauchy's second theorem's proof and also in previous theorems. So Cauchy's theorem, since P divides our center of G, so by Cauchy's theorem center of G has an element of order P, let it be Z. Okay, let it be Z. Let it be Z, that is Z power P is equal to 1. So take H is equal to, or you can say that C is equal to Z such that Z power P is equal to 1. Take a group where from Z is in fact an element of order of center. This is Z belong to center of G. So this is in fact a subgroup of center of G. And since center of G is abelian, so its every subgroup is normal in center of G as well as in G, right? So C must be normal in G. C must be normal in G. Since C is cyclic as well, so C must be normal in G, hence G by C is a factor group. Okay, G by C is a factor group, and you know that we will see that order of G by C is divisible by P, so by induction hypothesis it has a Sylow-p subgroup, right? Also we see that order of G by C is order of G by order of C, that is N over P, right? And you know P power alpha divide N, so this is P power alpha T by P, which is P power alpha minus 1T. Since P power alpha divide N, as we have proved that P power alpha divide N, but we need to show that P power alpha plus 1 does not divide N, to show that H is a Sylow-p subgroup in G. So order of H is P power alpha. So that's why N is P power alpha into some T, and C, order of C is P because it is generated by Z, and Z is of order P, so the corresponding cyclic group generated by Z is of order P as well. That's why n by P, and you know n is equal to P power alpha T, so that's why P power alpha minus 1 T. This means that P power alpha minus 1 divides order of G by C. So this implies P also divide order of G by C. Now look at this. Order of G by C is lesser than n. Of course, this is lesser than P power alpha T, which was n. Look, so order of G by C is less than n, and P divide order of G by C. Hence, by induction hypothesis, G by C has a Sylow-p subgroup of order P power alpha minus 1, right? Hence, by induction hypothesis, induction hypothesis, G by C has a Sylow-p subgroup say H by C of order P power alpha minus 1. Of course, order of G by C is equal to P power alpha minus 1 T. So the subgroup Sylow-p subgroup of G by C must be of order P power alpha minus 1. There is no relativity, right? That is, this shows that so this implies that order of H by C is equal to P power alpha minus 1. So this implies order of H by order of C is equal to P power alpha minus 1. So this implies order of H. Of course, here the H is a subgroup of G. Remember, because H by C is a subgroup of G by C, this implies that H is a subgroup of G. This is clear. This is clear. H is a subgroup of G. This is very much clear, right? So order of H by order of C, you know, order of H by C is equal to order of H by order of C, which is P power alpha minus 1. So you multiply this. So this implies order of H is equal to P power alpha minus 1 into order of C. So which is equal to P power alpha minus 1 into P. So this implies order of H is equal to P power alpha. Also note that order of H by C is P power alpha minus. So P power alpha minus 1 divide order of G by C, but no higher power of P power alpha. That is, P power alpha does not divide order of G. So that's why no higher power of P power alpha divide order of G. So since no higher power of then divides order of G by C, therefore no higher power of P power alpha divides order of G. Also, you know that order of G is P power alpha into something T. So that's why P power alpha plus 1 can never divide order of G. No need to write these two lines as well. You directly from here you can say that H is a Sylow-p subgroup of G. Hence, H is a Sylow-p subgroup of G. Right, this completes the proof. Okay, students, we have established Sylow first theorem and we have discussed in detail its definition, and similarly you can apply this theorem that every group of order n has at least one Sylow-p subgroup of where p is a prime divisor of its order, right? Like S3 has a Sylow-p subgroup of order 2, and S3 has a Sylow-p subgroup of order 3. S4 has a Sylow-2 subgroup of order 8 and a Sylow-3 subgroup of order 3. Similarly, you can understand the relation between a Sylow-p subgroup and the order of G, right? You need to revise this theorem, and next we will start Sylow second theorem and Sylow third theorem. And before proving Sylow second and third, we need to understand double cosets. So in the next lecture I am going to define double cosets, and we will prove 2 to 3 theorems related to double cosets to understand the proofs of Sylow 2 and Sylow 3. Thank you very much. Allah Hafiz.